Okay, it's 4 o'clock UTC, but in Topos tradition, we will wait 1 minute before starting, if that's okay. Perfect. Okay, Eugenia, whenever you're ready.
Okay, hello everybody. Thanks for being here and welcome to this month's MCATS seminar hosted by the Topos Institute. Thanks to Tim for doing the technical aspects. Today's speaker is Nuiok Dicaire, and she's going to talk about local monads and computational effects. Thank you very much.
Great. I will attempt to share my screen. Oops. Too fast. Is it working? I'm not. Aha, there we go. Is this working all right?
Yes.
Okay.
Well, I forgot to just tell everyone, sorry, that if you have questions, the speaker will pause from time to time to see if there are any questions, and you're welcome to type questions into the chat. And if it's a question that's a clarification question about what's just been said, then I will pose that question, and the other ones will wait until the end as usual. Sorry, Neil, go on.
No problem, thank you. Okay, hi everyone, thank you for coming. I also would like to thank the organizer for putting together such a nice seminar series for people like me to get a chance to give talks. I think that's pretty neat. Also, thank you, Eugenia, for all the hours you put into helping me make this talk happen and just kind of bring it up another level. It's really much appreciated. So hi, my name is Nuiok. I'm doing my PhD in informatics at the University of Edinburgh. And today I'm talking to you about localizable monads. And the idea behind localizable monad is that we're trying to define a new notion of how we can have local monads based on some internal structure to monadal categories. And before that, I should mention this is joint work with Chris and Carmen at the University of Edinburgh. So what is my plan for today? I will first talk to you about some motivational problem, just to explain a bit where I'm coming from with this and what is the kind of application that I have in mind for this type of work. After that, I will present to you kind of the central notion which we will be using to define this new notion of local and localizable monads, and this will be called central idempotence. And that will allow me to finally bring you the definition of and the notion of localizable monad. So that's kind of the first part. And then after that, to put things into a bigger context, I will talk about a more abstract characterization of localizable monad, and this will be in terms of monads, of formal monads in 2 categories. And then I'll come back to the motivational problem that I started with and see if we can kind of connect things now that we have all the framework that we need. So that's the plan for today. So let's start with these motivational problem. And before I really do that, I'd like to talk to you a little bit about the idea of monads. So I like to see monads simply as a way of providing context or providing objects and morphisms with additional context. And of course, I mean by monad simply the definition of an endofunctor, a triple consisting of an endofunctor and 2 natural transformations that represents the unit and the multiplication. I will try to get my pointer working. There we go. Okay, and we can, I mean, monads are used in a lot of different things, but in a more kind of computer science point of view, they are used a lot to describe things like side effects in programming semantics. For example, kind of the reading and writing from a memory store. In that context, it makes sense to ask questions like what kind of inner structure can we have, or what kind of monad structure can we define to talk about a sub part of these side effects? So if we have something that does not affect the entire state of our system, but only a sub portion of it. And that is the idea that we'll be talking about today. So one example that we can consider when thinking about this is in the context of concurrency. Say we have two agents, 1 and 2, Alice and Bob, that have some set of actions that they can do that can be kind of in a bigger context of networking or something, or in the security protocols, or simply, I don't know, baking a cake or something. The point is that they have their own set of actions that they can do, and that this combines together into a larger system. Now, if we have kind of the combined action described on the larger system, it would, and if that is defined as a monad, it would be nice to have a way of extracting, for example, the contribution of the first agent and have kind of a monad restricted only to the first agent that described their contribution. So that's the idea. If we would have kind of a large category with the large monad, can we have a restriction in some sense to define of this larger monad to a smaller monad? Another example, when we think of the category set, and we look specifically at the state monad, that can be used for things like talking about a memory store. But the point is this monad here is simply defined as kind of the maps. You take some object and you send it to the maps from S to blank tensor S. And we would like to have something that looks like some decomposable notion of underlying data. And there's not much here that we can work with. But if we look instead to something like this, where instead of looking at set, we look at this. I will accept this recording. So if we, instead of looking at something like set, if we look at something like set to the n, and then we look, well, instead of having just kind of S and an object just kind of A, we have clearly a lot more to work with, a lot more of this decomposable underlying data that we could do something with this. And this will be the idea. And we can then raise similar questions for categories like HILB or HILB to the n that can bring us to kind of applications as a quantum memory buffer, things like that. So the next step is to talk about this, really, that notion that will enable us to have this notion of localizability and decomposition over this structure. So we need to talk about this. And this will be called central idempotent, but this is not really the point that I'm trying to make right now. Before I get there, I want to just talk about what does it mean to be kind of, what kind of intrinsic structure do we have in a monodal category that we could use to achieve what we're looking for. So this is really what this section is about. Okay, so what do I mean by this? So I want a way of splitting up a monad into smaller monad. And I'm really looking for a structure inside a monodal category that will enable this. And yes, that will be called central idempotence. And you have some work on idempotence in monodal categories that you can find here. And if you want more information just about kind of central idempotence in general, you can look at the paper Tensor Topology that talks about this a bit more. It's talk in terms of subunits, but the idea is the same. Okay, so before I get into that, let's consider a specific monodal category with kind of some interesting notion of bigger and smaller. So let's look at the category where we have R is, well, first, let R be a commutative unital ring. And let's look at the category, the monodal category of R modules and R linear maps, with the tensor being the tensor of R modules and your tensor unit is the ring R. And in that context, I'm sure you have heard that you can have the notion of ideal. And that is an interesting type of internal structure that you have in this context. Moreover, you can have these ideals and you can require them to be idempotents. So when we have that, what do we get from that? Well, being an ideal means that you will have a map that goes from, I'm calling my ideal U, and there'll be a reason later on. So there'll be a map that goes from U to the ring R. We can also look at the map U tensor the identity on U, which we can define this way. And then we can bring the notion of idempotent. If we have idempotent, that means that U is equal to U squared, and we can define a map from U to U tensor U this way. And using that, we can show that actually in this case, we have that U tensor U is invertible. And the idea that I'm going to use here is like I'm going to use this idea and try to bring it up a level in a categorical context and see what we have there and what we can generalize. So the idea that I'm extracting from this are essentially that I need to have some morphism U from some domain U to the tensor unit, such that, well, this looks a bit ugly, but it's only really saying that the map U tensor, big U tensor little u, is an isomorphism. And if I tried to draw that, it would look something like this. So if we have U tensor U, and we decide to essentially apply the U, the little u, on one side or on the other side, then these two things have to be equal. And moreover, we need this to have an inverse such that if we start with some u, then we go from u to u tensor u, and that if you compose these things together, then you'll get back the identity. And this is what I will use as my definition of being a central idempotent in a symmetric monodal category. This bit is a little bit important. So the symmetric part is important in the sense that if we weren't, this still works in arbitrary monodal category, but we would have to talk about a bit more and say that, okay, to be symmetric, not to be symmetric, but to be a central idempotent, you would have to be kind of a central object in your category. So you will need to kind of include this notion of braiding for your central, a notion of braiding for your central idempotent. But just in the, wanting to keep things simple, I'm just going to define this for a symmetric monodal category for now. An important thing to note is that the tensor unit is actually a central idempotent. It's actually kind of the bigger one, the biggest one. So every other u is kind of included in that one. And I'll come back to that point a bit later. Another important thing to note is that the little u, the map u, is completely determined by the domain u, the object u. So we'll use any u kind of interchangeably. When I say central idempotent, I just mean some u, and I'm not making a distinction between the little or the big one. Okay, finally, before we move on from this, we won't really be using directly central idempotents. Usually we talk about equivalent classes, and we will say that U and V are, we identify them when there is an isomorphism M such that U is equal to the composition of M and V. Okay, let's go back to some examples. Specifically, let's look at a sheaf, which is a pre-sheaf of this sort, plus some nice gluing things that are not important for today. And let's look at the monodal category of sheaves over a topological space X. In there, we can talk about subterminal sheaves, which are things that are defined this way, that take some open V and sends it to either the empty set or a singleton set based on the relationship between V and some other object U. Okay, cool. if you use that definition and you look at specifically what it means to be a central idempotent, as the definition I just gave you earlier, you will see that this is ugly but can be made to work. We don't actually have to do that though, because we can also take a different approach and simply prove that in a Cartesian category, central idempotents are exactly the subterminal objects. Now, the reason that I didn't start with that, and I'm looking at the model category of sheaves, is because this will actually give us a really good intuition moving forward of what central idempotents are supposed to be. And that is because you know or don't know, but it is, if you dig back into your knowledge of algebra, it is true that subterminal objects are actually simply equivalent to the opens of X, which means that going forward, we can think of central idempotents as open subset of a hidden kind of base space that any symmetric monadal category comes equipped with. And that will be kind of the motivation going forward of thinking of central idempotent as this kind of structure that you have that comes with your monadal category. Okay, more examples. Let's consider set. Everyone likes set. If we are looking simply at a set with its Cartesian product, then the central idempotents actually aren't that interesting. It's simply kind of the empty set and the singleton set, which I'll just write as 0 and 1. But, and this kind of comes back to something I've talked about with the motivating example, if we look at set to the n, then actually here, the central idempotents are now a combination of 0 and 1s it's kind of hard to just say like that, but it kind of works like this. So if you have kind of set to the n, I mean kind of n copies of set. So if you have kind of 3 copies and you have 3 set, and you tensor that with a subunit that, for example, looks like this, that will give you something that kind of extracts the contribution from here, A and C. And I'll come back to that, that motivating example later on. Very important thing to mention, though, is the example of lattices. So in a meet semilattice, if you see this as a category, the central idempotents are actually all the elements of the lattice. And why I really want to mention that is because, in fact, there's a bit more going on here, is that central idempotents actually always form a lattice like this. And in your lattice, you'll have your top element, your largest one, and you'll have this lattice decomposition of opens, you can think as, of your tensor unit inside your category. And this is what we are going to be using to talk about monads. So before I get there, and before I talk about how we'll do that, are there any questions so far?
No, there don't seem to be any questions at the moment. Thanks.
Awesome. Let's put that away and let's look at what we want to do. So what is the plan here? We want to use the notion of central idempotent to define a notion of local monad. I'll do this first by using the notion of central idempotent to define a bunch of local categories. And then using all these categories, we're going to look for conditions that allow us to define monads on all these categories. And that condition is what we're going to call being a localizable monad. So this is the plan right now. In order to do that, I will first need to define some categories restricted to these central idempotents. So that's step one. I want a bunch of categories, essentially one for each central idempotent U. So we can do this. We can define a new category, and I'm going to call C restricted to U. And if you want to know more about how to define this and what that is, you can look at the paper tensor topology again. So how do we define this? Well, for objects, I'm simply going to say the objects of this new category are the objects of C. That's it. For the morphisms, though, I'm going to say that, well, if I have a morphism from A to B in C restricted to U, this will correspond to or be defined as a morphism in C from A tensor U to B. And so this is kind of where the important bit is. This is where the magic happens, because I didn't do anything with the objects. So really, all I'm really putting all the hidden bits is in the morphism. And then obviously, because I've defined morphism this way, I need to have a that will sense this morphism. So if you have in C now, if you have your morphisms F in CU, but then defined as U tensor, something from U tensor, from sorry, A tensor U, and then also G, well, you need to have a way of essentially taking a U and copying it and getting another one so that you can kind of fit all the things where you need to fit. And you can do that no problem, because that was the inverse talking about defined central idempotent. That's what you put here. And if you look at this and you're like, this is something, you're right, it is something, is actually the Localisable composition of the comonad blank tensor U. And if you're interested about this, well, I will come back to it later. And I'll talk about a little bit kind of the hidden structure that we have here. Okay, and if you need to define the identity, well, you just do kind of the object tensor, the central idempotent, and this will work. This will be a category. So what is kind of the idea that we have here? So I said that we can think of this, all these central idempotent as kind of this lattice structure hidden in your tensor union. But now what we've done is that for each of like the points of this lattice structure, we've defined a whole category that can go there. And so we have kind of this categorical decomposition of kind of this bunch of categories that form this structure. And so the next step, oh, and you can see this category C is actually kind of C restricted to the tensor union. So that's kind of the largest element that you have there. And the question we want to ask on this is, can we put a monad on each of these new categories? Something that would be like this. So assuming that we have some kind of monad that we start with on kind of the global, a global monad on C, can we find local ones on each of the internal structure? And the answer will be yes, and I will talk about it in a second. But before that, are there any questions now that I've defined all of this?
No, there don't seem to be any questions. Thank you.
Perfect. Let's talk about monads then. And this will, so far I've kind of been talking about, other stuff, but this is new stuff. This is stuff that I actually worked on, and the new definitions and new theorem. So this is it. So what we want to do is we want to answer the question, can we put a monad on each new category, that kind of the C restricted to U thing that I've just described? In order to do that, we will first find some condition of what it can mean to be localizable. And using that condition on what it means to be localizable, we will define the local monads. So if you stop and just kind of think a little bit, what would be the kind of obvious thing to put as a condition for what it means to be localizable? So you think, but actually this isn't how we do things, is it? We don't kind of, try to find the condition. We will try to define what it means to be local, see what doesn't work here, stuff that into what it means to be localizable, and say, okay, that's our condition, let's move forward. So let's do exactly that. Let's try to define what it means to be a local monad on C restricted to U. Okay, so we're working with the assumption that we have a monad T with like the unit and the multiplication on C. And we want to find a bunch of monads on C restricted to. For the objects, again, I'm just going to say it's the same object. So the object like T, U of some object A, I'm going to define as T of A. That's it. Morphisms. Okay, so what is T, U of some map F? Well, this T of U is something that will live in CU. And so it has to be something that will be kind of the form T of A tensor that goes to T of B. Okay, well, how do I get from here to there? Well, F is also a map in CU, so it also has the form of T of A tensor U to B. So that's good. We can just say T of F. But what we're really missing here is a way of kind of taking the U and putting it back inside the monad. So we just need that map. Cool. Assuming we have that, now we can define the unit and the multiplication of the monad by just kind of tensoring with the central idempotent U. And that will work. We just need this. So we will define a localizable monad to be something that provides us with what we need here. So we will say a monad T is localizable, so a monad T on C is localizable at a central idempotent U if for any object A there are maps, partial strength, I'll come back to that, but maps that essentially take the U and put it back inside the monad. Now, and that satisfies some compatibility acts. Now, partial strength here is important. There exists this notion of strength that essentially does the same thing as this, except that it's defined for kind of any A and B. So I'm calling these partial strength because I'm restricting it to, well, I'm only asking for U, okay? And then the compatibility axioms are exactly the same as being a strength, just adapted for kind of a more limited case. And I will say that a monad is localizable if it's localizable at all central idempotent U. Examples of that will include things like a strong monad, obviously will satisfy the case of being of a partial strength. But you can also kind of build up some other example. For example, if you have a monad T in a Cartesian closed category with this property, that will also work. But the point here is that, or the conclusion that we're trying to make, is that we have this notion now of what it means to be localizable. And using that, using what it provides us, we can talk about local monads. Okay. Are there any questions?
No, there don't seem to be any questions. Thanks.
Awesome. Okay, so what have I talked about so far? This is the talk that I promised you. This is essentially what I've covered, which was motivational stuff, then essentially just definition, 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 definition. But hopefully that gave you kind of some intuition of the logical step to get to a localizable monad, which again, are things that we really want to define with respect to the notion of central idempotent, which is a kind of internal structure to a monadal category. And from this, we can talk about local monads. Okay, but we would like all of this to fit nicely into a larger setting and kind of make connections to other things. And ideally, if we make those connections and use those connections to tell more about these localizable monads. So I'm going to now talk about what is kind of the main theorem of today, which is an abstract characterization of localizable monad. And then I'll go back to motivational problems. Okay, so this characterization of localizable monad, I will provide using monads or formal monads in some two categories. And the reason I'm choosing to do that with two categories is that you'll see that actually this is really similar. So there's clearly something going on there. So let's try to do that. Great. So what we're looking for is something like this. We know we have localizable monad, and we know that there exist things like monads in two categories, like is something that kind of does this and allows us to go from one to the other in such a way that kind of looping back and forth gives us something is equivalent. We end up where we started. So this is what we are aiming for. I'll talk a little bit about two categories in order to be able to talk about this theorem. But I only want to talk about two categories in the context of talking about monads on them. So this is what we call the formal theory of monad, following Street, which you can just kind of understand as repeating the theory of monads, but in arbitrary two categories. So what is a two category? Well, it will have two cells, things like A and B. It will have one cells, which are maps between, sorry, did I say two cells? Zero cells, which are A and B, maps between two cells or the one cells like F and G. And then two cells will be maps between one cells, which are things like alpha. Okay, and specifically for our purposes today, we will be talking about the two category that is a functor category between this, which are simply the central idempotent as a category, and the category of small categories. But these are actually two categories. And this is, again, this notation means central idempotents. Okay, what is this category? In this category, the zero cells are now two functors. The one cells are natural transformation between these two functors. That means that their components are themselves two functors for each u. And the two cells are now modifications, which means their components for each u are themselves natural transformation. Now I have to put a warning here, disclaimer, that this can get confusing. Just because when we think about these things, we're often like, okay, so zero cells, categories, and then one cell's functors and natural transformation. But no, we're kind of, changing up the level here, and we have kind of modification that will have themselves component as natural transformation for the two cells. So keep that in mind. Okay, let's talk about monads in a two category. So what is a monad in a two category? Well, it is a one cell from one cell like T, from a zero cell to a zero cell. So it kind of mimics the idea of an endofunctor. And it's a two cell, or two cells, two cells, should be an S here, that correspond to the multiplication and the unit. And these will satisfy kind of the usual monad laws in the two category. What does this mean for our purposes of defining a monad in this specific two category? And the reason I'm choosing this is because it's going to make sense. So let's look at that. We'll choose a zero cell that will be the functor that goes from the category of central idempotent to the category of categories. And for every central idempotent, assigns it the category C restricted to U. That makes sense. Now, when we have that, if we take T to be, so T is a one cell, but it'll actually be a natural transformation that will go from this zero cell C bar to C bar. And what that will mean is that because this is natural transformation, it will come with a family of functors TU from CU to CU. Similarly, if we have two cells, which are modifications, then these will correspond to families of now natural transformations for every u. So we'll have kind of mu of u and eta of u. And when we look at this, you might actually be thinking, well, this is kind of very similar to what we had with localizable monad, when we had kind of essentially just a family of these monads from CU to CU. And yes, that is kind of my point where I'm trying to go, is that this will actually be equivalent. So this brings us to the main theorem, which is, again, this is new results. And so this theorem says that if we start with localizable monad and we go to formal monad, we can do this kind of going top, essentially by using the definition of local monads. And we can also go back by, well, we have to, if we start here, we have to define a new kind of strength on this side. So the theorem says that for monadal category C, there's a bijective correspondence between localizable monad on C and formal monad in this two category. To go into a little bit more detail, the top arrow simply kind of follows by, I mean, it's a bunch of diagrams, but it really just follows kind of by definition of defining these kind of local monads. The bottom arrow essentially follows from the properties of the strength that we need to define to go from formal to localizable. And then going from formal to localizable and back to formal, the fact that this kind of brings us back to where we started, follows mostly from properties of naturality of the strength. Now, going from localizable to formal means that we start with some strength here, go here, and then we define a new strength here. And we want to kind of end up back in localizable monad with the initial strength that we started with. And the reason why this works is actually this strength that we define is going to allow us to recover the original strength that we started with in our localizable monad. So that's the main idea. Are there any questions so far before I try to talk more about what's going on here in this strength?
No, there don't seem to be any questions. Thanks.
Perfect. Okay. Then moving forward, let's look a little bit more in detail at what is happening behind this. So most of what I said before was like, oh, this arrow and that arrow, and doing this, it all follows by definition, by naturality, by this. The really kind of the only thing that we're missing is kind of, okay, well, a lot of stuff seems to be hidden in what is the definition of the strength. So what's the idea here? We need to define this new strength to go from formal to localizable. This means that for each V, that's a central idempotent V that is larger than the U. So this sounds confusing, and I'm really just saying it because it works for all V, but take V to just be kind of the tensor unit 1. So this is really just T, okay, kind of a normal higher level T, but it works at all levels. So we want a strength that allows us to put the U back in. And to do that, we will use, in fact, the fact that C restricted to U is actually the co-Kleisli category of the comonad blank tensor U on the category C. And this means that, well, we actually have this adjunction between C and C restricted to U, where we take this comonad blank tensor U on C, which will denote FG, and these are kind of the canonical standard functors that you will get out of this adjunction. But using this and kind of all the structure that this gives us, we can now define a strength as follows. So what do we want? We want a strength that goes from T of a tensor U and kind of gives us a U back inside the T. So we know that blank tensor U can be rewritten as the functors F and G. So we do that. Now you have to trust me a bit on this one, because we have asked in our formal monad that the one cells be natural transformation. We get that we can exchange the G and the TU and actually kind of change the V to a TU on the outside. So you have to trust me on this one, but this works. And then now that we are in CU, we can use the unit of the adjunction that lives in CU, and we can make it a GF. Using the naturality again, we can switch the TV and the G and the TU to a G and a TV. And now using the co-unit of the adjunction, we can make that go away such that we end up with precisely T of a tensor U. That's the idea here. And kind of that structure is kind of what is behind making these proofs here work. Okay, to conclude the talk, I would like to go back to these motivational problems that I talked about initially. So the first one I was talking about was this idea of concurrency. So if we have two agents, say 1 and 2, that have kind of a monad M1 and monad M2, and they have a specific bunch of actions that they can do, and they kind of combine them to bake a cake or something. And that represents, you have a monad M on kind of a larger category that encompasses all of this. And more specifically, I want to kind of narrow down a bit and say that what I really want to look at is the monad is called the action monad or writer monad on set. So what does that mean? It means that if you take some A, you assign it to M tensor A, where M is actually a monoid. So I'm going to use kind of the M to represent monoids here, specifically for this writer monad. Okay, but now if we look at the Kleisli maps of this, well, we can interpret this as something from, if we have kind of an input A, not only do we get an output B, but we also get some monoid M, which could, for example, represent like a log file of all the actions that you need to take to get the output B. And you can add some kind of more details and say, okay, well, we want some of these monoids to commute or not commute, or actually just kind of some part of them to commute. And we can add these restrictions. So what is the setup that we're looking for here? We want a category C, but we want to start with kind of the category C1 and C2 and the monoids M1 and M2. And we want a category C such that it has also a monoid M that we can use to define the writer monad, such that it restricts, and here by restrict, I mean specifically in the scenario I've been talking about today, which is restrict kind of to the central idempotents, using the central idempotents, to C1 and C2 with each their own monoids M1 and M2. Now there's a lot at play here, and I don't actually want to go into all the details of it, but let's kind of consider what is the essence of a construction that will give us such a C that can give us back this decomposition. So the general idea is that C will have as object essentially pairs of object from C1 and C2, and the morphisms will actually be kind of lists such that we've also added kind of some buffer in between some of the actions to take into account that some things we want to force, so we want some actions to not commute. This is what this is supposed to do. The idea that comes out of this is that then your central idempotent will be things that essentially will extract the contribution of only the first agent or the second agent. And again, there's kind of more detail here, but that is the essence of the construction that we have for this. And similarly, for the monoids, you'll get a monoid that in essence is composed of the monoids M1 and M2 in such a way that if you restrict the category C to the central idempotents, you will get back C1 and C2. And for the monoid, you'll also get back the monoids M1 and M2. So that is kind of the details of this construction for the first example that I talked about. The second example that I talked about was about essentially a notion of localization on the global state monad. So we started with this monad called the state monad on set. And we actually know now that set has central idempotent being kind of 0 and 1. Well, great. This is now localizable trivially because I cannot localize more than that. So it's already localized to kind of 1. Not very exciting. But let's look at this other example, which we've been talking about, which was set to the n. So if we look at the state monad on set to the n, then we actually get, well, something with a bit more, details inside. And we remember that the central idempotents on set to the n are actually kind of all the possible combination of 0 and 1. So you can have kind of 1, 0, 0, 0, and that would extract the contribution of kind of the first component. So in order for this to be localizable, we need to have a strength. The strength here can simply be defined as the curry of this map here. The point being that this is a little bit of detail, but it's kind of very straightforward to define your strength in this case. What it will give you, though, is that it will give you a monad such that when you localize it, you will get back, say you try to localize it like for the first component, you will get back something that looks like the state monad on set, but only for like S1 here and A1. So you'll kind of be able to go back to something that looks like your global set monad, but for each component. Okay, so that kind of, no, there's one more point. And then, as I mentioned earlier on, you can repeat this type of idea for both Hilb and Hilb to the n. And this will work kind of in the same fashion. And that kind of allows you to now kind of consider kind of some quantum applications, saying like, oh, do we now have like this quantum memory buffer on n qubits or things like that. But there's a lot of potential for kind of further investigation and further directions of applications here. Okay. A few other things that I'd like to mention before wrapping things up is, well, first of all, algebras. If you have monads, you might be interested in knowing what their algebras are. For localizable monad, so I'll just take a sip of water before I lose my voice. So for localizable monad, well, we know that these are actually characterized by formal monads in two categories. And there is a whole theory of how to get the algebras from that kind of formal theory of monads. So if you follow the recipe, you will get kind of some algebra structure. It's just not a bit too detailed for something like today, but you can do it. Another thing to consider also as an area of further research is the notion of commutativity. So if you have kind of two central idempotencies, and think of them again, we want to think of them as open sets, but if they are kind of disjoint open sets, we would expect that if kind of this represents some side effect or something in a computational program, and the other one represents something else, that if they are disjoint, well, they should commute. And this is the notion of what it means to commute in this context with the strength. So we would like to investigate kind of what we can do a little bit more here in examples of application, and then consider other kind of connections to other notions of modularity on monads, like a graded monad or parametrized monad, which is kind of a dual aspect of things, but we think we should be able to kind of merge them together, kind of talk about locally graded monads or something like that. So that's pretty much it. This is the paper about this is going to appear at CSL. You also have a first version already on the archive. And if you have any questions, I'm happy to try and answer them.
Thank you very much. So if anyone has any questions, then please type them in the chat to me, and then I will pose them. And there is, I think, a question, which is, do you know if there is any link to simplicial monads, since the localizable condition looks like something you could impose on the check nerve of a cover?
Simplicial monads?
Mm-hmm.
I do not know what a simplicial monad is, so maybe. Yeah, I'm sure this has a lot of application, but yeah, I just don't know what it means.
Would this person who posed the question like to say quickly what they're thinking of? What's a simplicial monad? They mean a simplicial object in the category of monads.
Okay, we have to go up another level. I'm stuck at what is simplicial.
Okay, well, that's something to think about for some other time.
Yes, definitely. Thank you for the question. I'll have a look at what that means.
Are there any more questions? Great talk. That's
happy to hear that.
Question. Any more questions, anyone? If there aren't any more questions, we can just, oh, maybe there's. The main theorem, here's a question. So this is about the main theorem that says that there's a bijection between localizable monads and certain formal monads. And the formal monads form the objects of a category. Is there a notion of morphism between localizable monads? And then is there an extension of the theorem to an equivalence of categories?
Can you say all of that again?
It's about the equivalence, the main theorem, that you had a bijection. Do those things form categories? And if so, does that bijection extend to an equivalence of categories?
I'm not sure. Potentially.
Okay.
Yep. Sorry, I I can't think of it like that, but maybe that could be interesting to look at.
Good. And then another question: what are central idempotents in Hilb?
I should know this. What are central idempotents in Hilb? Kind of the same thing. So you have kind of your kind of zero, which is just kind of C, and just kind of a zero, and you have kind of C as your one, but you don't have anything else. So you have to kind of update to Hilb to the end to kind of have kind of 0 and 1s to kind of have something more interesting to decompose over. But it's the same idea.
Okay, thanks. Another question. Thanks for the great talk. Is there a way to consider the converse of when compatible monads on C restricted to U assemble into a localizable monad on C?
Right. That is a good question. I mean, if you have just like, because we're really looking at something that has kind of a pre-existing notion. So you need to have a monadal category that has that decomposition of this in terms of the subunit, the central idempotents. So if you have that, then I suppose you would kind of, be able to build them back up. But exactly what would be the condition to make sure that if you kind of have something local, and is that the right thing if you start with something local, is that the right thing that is part of something bigger? I mean, I don't have kind of conditions right away. But yeah, I think it's kind of a question of just looking at, well, are we in something that, or do we have a monad kind of correctly defined on something that exists in something bigger? But I don't have kind of a set of conditions right away to say, oh, well, if you satisfy this, then you're in something bigger.
Okay, great. Are there any more questions? Okay, well, if there are no more questions, let us thank the speaker again. Yay! Woo. And if anyone would like to hang around and have a chat, this is the point where the speaker is off the hook. So we're not going to harangue the speaker with more math questions, but just to say hi, have a chat, and a virtual coffee. So thanks very much. I think that recording will stop now. Is that right? And the live streaming